Okay, so now let's start. And let's start with, first of all, to put us into context. What is exactly the problem that we're trying to address in this project, Sunrise, that we've been working on for so long? Basically, we see the problem here on this overview. We see here the disadvantages of non-automated, privately owned, fuel-powered vehicles. And this will probably not be a surprise to any one of you here. This is situations that you're probably very much aware of since you're experts in this field. It's streets filled with cars, taking up a lot of public space in our cities. Also, traffic congestions and pollutions that all these vehicles cause. And also very important, aggressive drivers or distracted drivers, intoxicated drivers that seriously jeopardize the safety on our public roads. And it won't be probably a surprise to you either that a large part of the solution is thought to be this kind of systems, what we call in the European arena CCAM systems. That stands for Cooperative, Connected and Automated Mobility. So these kind of systems are hopefully going to bring a large improvement on the problems or the disadvantages that we saw on the previous slide. So far, not much of a surprise, I would say, to most of you. But now comes the challenge, and that's the challenge that we've been facing for the last 3 years in the Sunrise project, and that we're trying to address. And that is how to assure the safety of these CCAM systems. That's what we've been dealing with basically in the last 3 years in our consortium in Sunrise. So for that, we started off with this vision. We've been showing this vision around the world on many events and congresses to show, and now also for ourselves to get clear what our vision is on this project. So here we see that the Sunrise and its framework, or well, the main goal being developing a harmonized CCAM safety assurance framework. And that framework is a central element within a large group of stakeholders that each have their own interest in this framework. For example, vehicle developers, as some of you are with us today, they will ask us the question, what scenario should I test my automated vehicles for? And also very important, and many of us here today with us are certifiers and regulators and independent assessors that ask us, how should I assess the safety of automated vehicles before I can put my stamp on it or before I can release it onto the public road? So a very important stakeholder of this framework as well. Then there's others like researchers or tool developers that can ask us, how can I make my tools fit to those of others operating in this field? Okay, so this is the vision that we had at the very start of the project. Also, we're not operating on this alone. We're not on another silo that is creating another approach. We highly connected to other entities worldwide. For example, twin projects like V&V Methods in Germany, or the Sakura project in Japan, of which we have some representatives with us today as well. And also people from AVSC, also one representative who used to work at AVSC. That's the Automated Vehicle Safety Consortium in the USA. Just a few of the entities to which we highly connected during the entire project. Okay. Total runtime was 3 years in total. We're about to finish in August. We will finish the project. And the total budget was about 13 million euros. So on the next slide, we see the work plan that we applied in all of those 3 years. And I won't go into much details right now, but in the center part, you can see again that safety assurance framework that we are developing in Sunrise and that we'll present to you today. And we can also see that's basically based on 3 main components: a method, a tool chain, and a data framework. What that exactly means, we will see later in this in today's presentations. And at a certain point, we also put this framework to the test by a series of relevant and realistic test cases. We'll also see what that means exactly more later in the presentations. I don't want to go too much in more details, because on this slide, we explain the high-level results that we achieved in the Sunrise project. This slide shows you that we created this safety assurance framework, which is a harmonized approach for safety assurance of CCAM systems, and very much related to the documents published by the UNECE It's based on that, the new assessment and test method. It's based on that document published by the UNECE. It's also for all vehicle types on the public roads, and all SAE levels can be addressed by that. And SAE levels are different levels of automation. You can also see that the safety assurance framework is based on a few pillars. And the first one showing the properties of the framework. So, for example, it's based on scenarios. We use scenarios to assess the safety of these systems. It's also based on a term called ODD, and that's operational design domain, the domain in which this kind of vehicles are supposed to work and to operate. It's also multi-environment. That means that these scenarios in these vehicles can be tested in multiple types of environments, like virtual simulation or proving grounds or anything in between. And it's future-proof, which basically means that it can handle new regulations or standards in this field, and it can also handle future scenarios that might pop up in the future for these types of vehicles. Then we also see another pillar called methods. That's a strong pillar. For example, with methods for target setting or for scenario selection and scenario allocation to test environments. Or we have a large set of tools, for example, the scenario-based databases on which, from which the scenarios are extracted, but also a scenario hub, what we call a data framework. We'll learn more about that today as well. And this data framework provides one central access point, providing access to a wide variety of external databases that are connected to it. We'll see examples of that later. And then the last pillar here on the right side is about metrics. We also developed a lot of metrics, and we made use of existing metrics, for example, for the scenario quality, database quality, or simulation model quality, or ODD coverage. We'll learn more about that in today's program as well. At the very basis, we see a few topics on which this whole safety assurance framework is based. For example, an ontology, which is basically a common language that ensures accurate internal and external communication between the different elements and stakeholders of this framework. And then we also, as I already mentioned, we aligned internationally with many entities that are affected by this framework or that would like to make use of this framework. For example, type approval authorities, also many representatives with us today, the European Commission and its member states, consumer testing organizations like Euro NCAP, standardization bodies, and also twin projects and initiatives. Also, of each of these entities, many representatives are with us today, so I'm very happy to see that. Also, it's very much aligned with certain regulations and standards. I already mentioned one, that's this UNECE new assessment test method, but also standards by ISO, by ASAM, by BSI, or SAE. And at the very bottom, you see some use cases. And we used a large number of use cases to put our own safety assurance framework to the test, to make sure it works well, and to demonstrate also that it's working. We'll see details about that later in the session today as well. So this is a high-level overview of the results of the Sunrise projects. Now, this is the consortium that worked on this project for 3 years. Again, here you see representatives from different types of stakeholders that each have their own interest in that framework that we created. And we didn't work on this alone, as I mentioned. There's various ways that we cooperated with other entities in this field. So here you see the 4 most important ones. For example, we continuously cooperated with vehicle safety bodies. For example, with ISO, with ASAM, with UNECE, with the European Commission and its member states. Here you see a very good example where people of the Sunrise Consortium are working together with people of the RDW. And that collaboration will also be shown later today. So very nice way of collaborating there. Type approval entity that already applied our framework in their environment. We'll see the results later today. Okay. Also, we did a lot of cooperation with this block with twin projects and initiatives. I think the best possible example is probably here. This picture was taken during our midterm in Brussels in April last year. And here we see people, representatives from TRIM projects from Sakura, from BNV Methods, from Transport Canada, and from the Katri Institute in Korea, and also from the Automated Vehicle Safety Consortium in the US. They were all with us on this day in Brussels to give us feedback on the draft version of our framework. So that was a very important moment for us as well. And that shows that we internationally cooperated very well. Then there was a thing called Expert Platform. And this Expert Platform was a group of about 150 people, individual CCAM experts, with which we had about 10 workshops. And in those workshops, we presented the intermediate results and people gave us feedback. That also led to a lot of input again to be processed in our framework. And then, of course, there's the wider public and CCAM community to which we disseminate our project results. There was also a continuous effort done during the project. So all this shows you that we are not another silo. Absolutely not. We are a harmonized new framework, but highly harmonized with other entities of relevance in the rest of the world. Now let's have a short look at the agenda for today. You can find it on the back of your badge. So we will have the same overview there, but I'd like to highlight a few topics on this agenda. These sessions indicated here in blue will give you a high-level introduction into the SAF, the Safety Assurance Framework, and its blocks. So that will happen in these sessions here. Then we will dive a little bit deeper into certain topics on these elements in these deep dive sessions. Okay, and then there's after lunch we will have an important session, SAF demonstration, in which we show a use case and how we used that use case to put our own SAF to the test. And we'll see the demonstration results of that in that session. And lastly, I'd like to highlight these sessions here, which are not sessions, they're breaks. We'll have a morning break, afternoon break, a lunch break, and even dinner. And that will be in a different area in the same building. So we have to go to the back of this building where you will find this area here with 2 lunch rooms. And that's where the exhibition area will be. And there you will find things like a large touchscreen like this one, another one, to play around with our handbook. You will find 5 roll-ups explaining the SAF. You will find 9 roll-ups demonstrating the SAF. And you will find also some desktop demonstrators there. Okay, so that's what's awaiting for you in this exhibition area. We'll see that later in the first break. Yeah, that's my part for now, general introduction. I'd like now to give the floor to John-Frederick Reunwald from Chalmers Industrietechniek. And John-Frederick, based on the handbook that we see there, he will give, no, sorry, not based on the handbook. On the PowerPoint slide on the main screen, he will give an introduction to the SAF. So, John.
Thank you very much. Thank you very much, Stefan. And it's forward here, on here. So, thank you very much. I'll now have a short introduction to what we're today, all of us are experiencing, the Safety Assurance Framework and the harmonized CCAM Safety Assurance Framework. What we have done here, and I'll talk a bit more about, is the different parts here, the input, the in-service monitoring system, and the actual SAF, the central part of this Safety Assurance Framework, how to use, audit, and then some, as Stefan also explained, some fundamentals and alignments here. At the end, we will take a brief look into the online interactive handbook that is available for all of you already today. We already have launched the 3rd version, so it's free for you to use it interactively. But I'll come back to that at the end of this presentation. So the NATAM methodology here is that we have the Safety Assurance Framework, the Safety Performance Assurance, where we have input about ODD and behavior, the external requirements and test objectives. We have also loops with the in-service monitoring system. And later on, once we have done the SAF, as we will explain today, we can also have a possibility for you as certifiers to do the audit or tool developers or whatever. So the if we gray out and focused into the input. The important thing is that we have a joint understanding about the content, the ODD, the behavior, what we aim to test in this SAF methodology here. There might be external requirements, except the ODDs, also about which type of cars or vehicles or whatever. So all this is being set in the input to the test methodology. And we're, even though we today will demonstrate the SAF, you have to remember it's a test methodology and not the actual test. So the input block provides data to be used in the other SAF blocks. So that's how we develop the different ODDs or behaviors, etc. The next block that sets the scene for the SAF is the in-service monitoring system. And we have a lot of data, a lot of input from the ISMR that we need to understand. And that is in the SAF, it's one of the feedback loops where we have situations and during the SAF deployment system where we can understand the content of what is actually the SAF or the CCAM system, how it works in these environments here. For example, we can use recorded information for future updates and do another loop in the design of the CCAM system. And then we have the central part, where we will do most of our talks today from the other presenters that I will deep dive into a bit later. This one, the central part, as you see also in the interactive handbook, this is the central part with the 3 blocks, the scenario block, the environmental block, and the safety argument block, where we also have put in sub-blocks here. And through the day, we will deep dive in these different sections, scenario, environment, safety argument, with separate sessions for deep diving into these ones. And this is the central part of the SAF for the CCAM system. So that is for today the main focus of the final event, the central part. Once we have done the SAF methodology, the workflow through it, we have also set requirements for the audit, where we will do the safety management approach and the development process, the tool makers, the OEMs, etc., can use the SAF to perform a good evaluation of how this tested vehicle or object performs in a good way. The fundament that Stefan mentioned, the basis for the SAF, is done by these, but not only, but these 4 fundamentals, the UNEC, the NATAM, the basis for the process is NATAM based, the AR157. We're also, as already been mentioned, using the ISO fundament, the ASAM, and the BSI. So the basis, since we aim to have a harmonized safety assurance framework, we need to have all these different pillars available and worked in the process. And we will come back to many of those here during today when we do the deep dives about the process. So as I end on my introduction, let me give you a short introduction to the handbook, the interactive web-based handbook that is already available for you. So this is in real now from the web base. So if you log into the Sunrise, you don't have to do that now, but if you want to do that, if you log into the official Sunrise homepage, under tools, there is a handbook version 3 now being launched, and this is where we are now. Yeah, now you can change to, so this one, I will talk a few minutes about brief introduction, how to use the handbook. And then during the exhibition, you can easily also test the handbook downstairs or on your laptops here. So if I click on the high level, the landing page is where I just showed here the content here. And this is then clickable. So we have the glossary where you can find used terms here. And this refers to the deliverables that we are already have been published. We will deep dive into this later on. We have the data framework that will be explained, and we have the central safety performance assurance. If you want to go into certain of these sub-blocks, you can click on any of those, and the homepage will then focus on in this case, for example, the format or the coverage or whatever, and then we will change. And you will have more deeper instructions or explanations about this. During the day, also, I want to indicate that if you have any questions or comments from your side, there is a possibility for submit feedback. So if you click on the submit feedback, you can write any comments if you think this is good, bad, or any functionality or whatever. Another feature on the interactive handbook that is of also great importance is this chatbot that we have indicated. So in this case, this chatbot, the infobot, uses all our published deliverables. So if you want to have any questions here, for example, if I type in here, what is the safety assurance data framework, the stuff, can you explain me the Sunrise data framework, and post this question? It will look through all our now up to today published deliverables and give you an answer. Now it's thinking a lot of material. One question. Then it will give you an answer related to the deliverables that we have. Yep. The handbook, the interactive handbook, will be administrated for 3 more years during paid by this project and maintained by Ertico. So it will be so. In short, there are some explanations here based on, for example, the deliverable that refers to. I just took one example, the data framework, but you're free to take any questions. As all of you are engineers, I suppose there will be a lot of interesting questions. Maybe not all are engineers, but so please test during the day or when you're home the chatbot and have a feedback on that one. And with that, I think I will hand over to one of my colleagues here, Jason, that will introduce the deep dive into these different sections here. Thank you very much.
Okay, so this button. Yeah, so I'm going to cover the next 10 minutes, which is an introduction to the scenario block. And then later we have dedicated task leaders and the people in charge of those individual blocks within the scenario block. So they are going to give you about a half an hour or so deep dive. So on this one, I was going to do it through this interactive handbook. So let's jump onto here. Okay. And so I'm going to click into scenarios. So what we are going to do is to focus in the central part, which is the performance assurance. And you can see, even before we enter the scenario block, there are 3 main elements, which are scenario, environment, and safety arguments. So that means at a high level, to perform this performance assurance workflow, all you need is a set of scenarios executing in a test environment or in a set of test environment. And then in the end, we consolidate those safety evidence that we collected through this execution, through the consolidation into evidence, and then allow us to make the decision whether it's pass or fail. So this is at a high level our Sunrise safety assurance framework in 1 or 2 sentences. But let's have a look at the first block. So let's have a look what's inside this scenario block. So scenario block, actually, you can see it has 3 individual subblocks, which are titled create and format and store. So for your information, create and format currently are outside the scope of the Sunrise project. Sunrise project starts from the second half of the interaction of the store, which later you will know that is what we call the Sunrise data framework. Nevertheless, the create and format are integral part of the safety assurance framework. So we are going to cover it anyway. So let's first have a look at the creation. So in order to have scenario for testing, first we have to create the content of the scenario. So the creation of the scenario, very well known in the industry, we have summarized there can be 2 main branches. One is through data, so we call it database scenario generation method, and the other is through experts knowledge, so what we call knowledge-based scenario generation method. And you can read a lot of publications by various entities covering certain part of the data or knowledge base. So for example, data, you could have past accidents, and you can analyze the statistics and to create similar scenarios that represent some accident hotspots. Or you can, through the knowledge base, for example, if you have in-house safety experts on a specific system, and such experts can then go into the system architecture and then derive some of the scenarios that can test the weak points of such system architecture. So those might be the knowledge-based scenario generation method. But at this stage, we are mainly concerned about the content or the semantics of what we want to represent in the scenario. Right now, the scenario is still in a loosely form or in some in-house format. In order to make them exchangeable and shareable across this kind of collaborative environment, we have to actually then format the content into different scenario description format. So in the industry, there are the most latest update. We have identified 4 different formats covering different abstracting levels. So they include functional level, abstract level, logical level, and the concrete level. And as an example of the concrete level, so for example, the open scenario, ASEAN Open Scenario 1.x, or now it's called XML, maybe a very detailed, very long description using XML format. This is very good for example, simulation execution. But then if you want to share it with other stakeholders involved in this whole safety assurance process, they might want a more human readable format. So in that case, we have to actually have a coherent alignment between how you derive scenarios from the higher abstraction levels. They might use a natural language format. So for example, the British Standard Institute, the BSI Flex 1889 is a natural language-based scenario description format. So how you go from those high level to, for example, the ASEAN Open Scenario XML Open Drive is a quite key important focus on this format. But again, create and format are currently outside the scope of the Sunrise, and the Sunrise story actually starts from the store. So the store actually is basically a storage or access to a storage of scenarios. So it allows user to actually, in the Sunrise scope, we have created this data framework. So allow user to have one access point. And on the other side of this data framework, we have all the qualified individual databases, starting from our partners, but also later we can open up for also other third-party databases that are not directly involved in the Sunrise consortium. If you are qualified, you can also be connected to the data framework. So there are quite a lot of requirements that dictate whether or not you are qualified. So for example, you have to actually support common standards. You have to support harmonized, standardized ontology as such. But if you are qualified, then the user, later on when we go to the environment block, you will see that the user will then be able to query our Sunrise data framework, and the data framework will then query those individual database, and using this ODD behavior input at the bottom. So those are the user input, and then then those created formatted scenarios stored in individual database will then be retrieved. So we will have a bit of introduction later on when we go to the environment block, talk about this data framework and this forward and backward arrow, and also this query process. Yeah, so basically this is a very quick introduction of the scenario. So just to sum up, we create a scenario, we format them, and then we store them in a database, and that database in the Sunrise scope will be then part of the connected to the Sunrise data framework for user to access scenarios. So this is a quick summary of the scenario. And now I'm going to hand over to my colleagues to talk about the deep dive on those 3 blocks.
Speaker. Main stage. Okay. Hi, hello everyone. My name is Jobs Beckmann. I'm a researcher at the Institute for Automotive Engineering at the Technical University in Aachen, and I'll start giving the deep dive on the scenario block. So within this deep dive, we'll cover 3 different topics. So I will start with the scenario formats and ontologies, and then I'll hand over to my colleagues to cover 2 additional topics, which are the scenario quality metrics, and then a very interesting view into our data framework. So let's start with scenario formats and ontologies. And Stefan already hinted at this at one of his slides in the beginning, but it is very important that we establish a common language, a common understanding of scenario content between different stakeholders, tools, databases, and so on, so that this content is understood in the same sort of manner at every point within our safety assurance framework. And in the context of the scenario block, as was already mentioned, we kind of start at this store level, so at the different databases. So the first kind of step is to ensure that all these different databases have a common understanding of the scenario content, so that they can talk with the data framework that we have developed, and through this data framework with the different users of the safety assurance framework, as well as also make sure that they can communicate with each other. So in order to solve this, we wanted to introduce, or we have introduced, I think we have, I can say this now at this point, a harmonized ontology to solve this problem of having understandable information exchange between the different points of the safety assurance framework, and to allow really this data framework to be able to be created. So maybe one additional important term, and maybe kind of a differentiation, is between a taxonomy and an ontology. So you can think of the taxonomy more as of the vocabulary of the language that is used. And one very important starting point we defined right from the beginning was that we don't want to introduce or want to start building already have been a lot of initiatives within the context of ASAM and different ISO standards that have already looked at defining taxonomies for scenario content, both for like the ODD as well as behavior of different actors in a scenario, so that we in the Sunrise project don't need to come up with like a new vocabulary that nobody understands, but we can build upon the basis of the vocabulary that has already been established in the industry. So this was our starting point. And then in order to turn this vocabulary into a real ontology, we need to look at the different interactions, interconnectivity of the different components or that have been defined in the taxonomy and how they relate to each other. So this was our main challenge. And in addition to that, we have identified that there are different levels of abstraction you might need for your ontology. So if you want to just have some basic tagging that you want to do in your scenario database, so that at the end you can get some valuable scenarios out of this. You might not need understanding to be allowed to be represented by the ontology that you might need if you have some other application. So this is why for the actual for the actual use of the ontology, we rely heavily on the open label standard. So the open labels within this ASAM standard, there's already an ontology defined, but also more importantly, it also defines a JSON format that allows us to transmit information of the ontology. Also, what parts of the ontology maybe a certain scenario supports, or what content is present in the scenario in this JSON format. And this JSON format allows us to layer different ontologies of different abstraction levels on top of each other, so that you can use multiple ontologies. So this is why we have really chosen to on the application side to focus on this. And then for more complex applications, we have then really, based on the ISO standards, gone about and created based on this a new harmonized ontology. We mainly focused here on the ISO 34503, which defines like a taxonomy for ODD, as well as 34504, which defines or which adds onto this with more behavior content as well. Sorry. And both of these also inherit a lot of the ideas and content from predecessors like BSI standards on ODD taxonomy, for example. And then you can think about it like this, that there are within the ontology, there are different like rough components. So we need, of course, to include some ODD content. So what is the behavior that the CCAM vehicle is traveling within? So environmental conditions, scenery elements like roads, for example. And we also need to define, if we want to look at a scenario, we need to define the different behaviors of the different actors. And we also want to include meta informations of the scenario as well in the ontology. What we then did is we looked at, okay, how can we interconnect or relate the different terms in this taxonomy, and can we define different attributes that different concepts within this taxonomy might have, like different types, state, quantity. What are kind of the measures that we use for these terms? Can we define them? And then can we define different instances, for example, of these concepts? Here I have an example for simple rain. We have a rainfall, which is a type of weather with with it is a type of environmental condition, and this rainfall has an intensity, and in this case, so this intensity is an attribute of this rainfall, which is in itself a scalar value, and this scalar value is defined as 0 millimeters per hour in this case. So then we call this specific instance of rainfall no rain. And this is just a very simple example how these interconnections work. This we then have defined for all the different elements that were described in the different taxonomies that we looked at. And using all this, we then get a usable ontology that we can use as the basis for the data framework and other components, for example, the simulation execution we'll look at in the environment block. And with this, I would like to hand over to my colleague to introduce the metrics.
Hello. Thanks, Jobs. So a little bit different topic about metrics. This is a kind of metadata that we want to add to the scenarios that can help you to do some queries. If you want to have some scenarios with a certain exposure or complexity or whatever. So what we did in Sunrise, we first did a literature study on what are the metrics that are available in the literature. Well, there are many. But there are also many where we thought, okay, maybe we can work on that. And that's what you see here. So these are the types of metrics that we developed, that we worked on in Sunrise. So there are more, we identified more types of metrics, but yeah, we could not work on all of them. So I will just go through them one by one, except for coverage. I will deal with coverage later today. So there's still kind of a cliffhanger. So first about testing purpose, and then we divided that into 3 more metrics. So first is scenario relevance, and the way that, at least within Sunrise, we thought about that is that we said the riskier a scenario is, the more relevant it might be for testing. And then risk is similar to ISO 26262 is defined as exposure times controllability times severity. So we developed a metric to calculate this. Second component of testing purpose metrics is scenario criticality, and this could be done on classic methods, classic metrics like time to collision, post-encroachment time. And what we Well, then actually you have 2 options. One is to define those metrics, the values based on scenarios that you have not simulated yet, but then you depend on initial values, for example, initial time to collision. Or you do this for a test scenario outcome. So when you simulate it, you can have the minimum time to collision, for example. Of course, you don't know that when you did not simulate it yet. And there are different use cases for both of them. So in some cases, you already want to know what is more or less the criticality before you're going to simulate. And in some cases, you want to do that afterwards, in case you want to do some iterative testing. So we worked on both these parts in this project. And the third part is on scenario complexity. And then complexity can be defined, well, it's a bit subjective. And that's why this metric is highly flexible. So the way it's developed, it's just based on some weighting of factors. And these factors can be whatever you want. So it can be, well, including environmental or road complexity. So for example, the number of lanes or the number of road signs, I don't know, or the number of potholes, well, you can name it. And also some dynamic entity complexity. So for example, the number of road vehicles, the type of road vehicles, perhaps cyclists, you want to give a higher complexity score than cars, I don't know. And the idea is that you can then define some weights for each of these factors, and then you get a complexity score. So it's highly flexible, and depending on the use case that you want. So it's not that for a scenario database you have one complexity metric. You can have multiple. Perhaps it depends on your use case. So that's what we worked on as well. When I go to scenario description, we considered 3 different possibilities. One is that the scenario description is complete. Well, we are all happy, then we show a green sign. It can also be that at least the information that should be there is there, but then some optional information is not there. Then we will give it the color amber, which stands for missing information. But it's still okay. You can probably run the scenario in a simulation, but you probably don't have all the metadata that you would like to have. And we also have the incomplete status, which means that something is missing and actually it's not good. We should even not report this scenario. If you query a scenario, probably this scenario should not be returned to you because you cannot use it to simulate or to test. Then I go to scenario exposure. So this quantifies how likely it is that the scenario occurs. And what we looked at least within Sunrise is mostly at the parameter level. So how likely is it that you encounter a certain scenario with some parameter values? And the way to do that is to construct a probability density function of those parameter values. And that can be done in multiple ways. There's a lot of literature on how to do that. So that's actually not what we where we developed something new. But we looked at what are good methods to do that. And one thing that we at least thought is it's good to also look at the dependency between the different parameters, because obviously they depend on each other. And one classic way, I would say, is to use kernel density estimation for that. It's okay, but it doesn't scale brilliantly. So that's why we also looked at an alternative method, which is then would be the use of normalizing flows. That's used a lot in generative AI. And what it does is, in very simply said, it just transforms a super simple distribution, so like could be a Gaussian, to a highly complex function through a mapping. Usually neural networks are used for that. And this transform density is then actually quite capable of modeling the dependencies of the scenario parameters. So that's, yeah, we have shown in Sunrise project that this can be a promising method to estimate the scenario exposure. The last method that I want to discuss right now is the scenario similarity of scenarios or dissimilarity of scenarios. This is also already quite some literature on this topic, but what we have seen in the literature is that it mostly focuses on the trajectories of the individual vehicles, and then it applies some metric to quantify the differences between these trajectories, so dynamic time warping or something like that. And what we thought within Sunrise is that might be an okay method, but actually, usually we are not interested in the whole scenario, but the most interesting part of the scenario is probably the most critical scene or time instant in that scenario. And that's where it really matters how similar scenarios are. So that's what we did. So a metric has been developed that prioritizes the most safety critical scene. And then how that is defined, yeah, that's can be defined in multiple ways. So that's a bit flexible. So it still considers the complete trajectories, but then only looks at the most critical scene. So a new method has been developed for that and also published. One more slide. This is the last slide for me. So that's where the metrics are used. And actually, it's not the full story, but since we are now with the scenario block, it can be used in this part to just add, I already mentioned, add these metrics as metadata to the scenarios. But it can also be used for the audit. For example, the audit wants to know, okay, what is the exposure of the scenarios in this database, or what is the criticality of these scenarios, etc. Actually, the metrics are also useful in the rest of this safety assurance framework, but that will be covered later. So still a bit of a cliffhanger. I think now it's part for the next story, data framework. So I hand over to Marcos.
Okay, thank you, everybody being here. My name is Marcos Nieto. I'm with Vicomtech, and I will be talking about the data framework. As you can see, the data framework, and has also been explained before, is a cloud application that has been developed in the context of this project, the Sunrise project, that works as a federation layer to interconnect with external and existing scenario databases. So in a nutshell, the Sunrise data framework operates as an interface to other existing scenario databases. That means several things. One of them is that the data framework doesn't contain or store the scenario content itself, but rather works as an interface so that the users can use the scenario data framework to access the different existing scenario databases from a single point. Of course, the users must have valid credentials to access these scenario databases. So Sunrise Data Framework doesn't provide credentials to users. The user need to already have these credentials, but unifies the process of query creation. That means that the user will have to create a single query in order to find the scenarios of interest at the different scenario databases simultaneously. Some of the features of the the Sunrise Data Framework is the secure user and SCDB credentials management. So in Sunrise Data Framework, it is not store either the credentials of the user. We use modern technology to bypass this authentication information through the interface so that we don't store private information of users or the scenario databases. It's then possible to search for multiple in multiple scenario databases simultaneously. Of course, we have developed different components at this software platform to simplify the life of the user, so that there is a query user interface that helps the user to create and build queries using and following the ontologies that have been described by my colleagues before. In order to find these scenarios of interest. We also have some components for visual analytics, so we can retrieve the content from the scenario databases and explore the results of the queries so that the user can then select what are the scenarios that might be of interest for the subsequent steps of the SAF, namely the environment step. To make this a reality, we needed to of course, implement a standardized API, and that has been a effort not only from the perspective of Sunrise, but also from the scenario databases hosts, the owners of these scenario databases, in order to connect to Sunrise, because we have to negotiate the API definition. This is already in place, and I believe it was also mentioned before that it's possible to onboard the Sunrise data framework by following some steps we will see next. So it's possible for other scenario databases not being part of the Sunrise project to join the Sunrise data framework later on by following the onboarding process. At the moment, the data framework is a software deployment in cloud instances. That means that it will be up and running through the internet. As of today, there is a prototype working. There are still a couple of months yet for the Sunrise project to finish, and the final deliverable will be this platform. The picture just highlights the main idea of having like a central piece of interface with other existing initiatives, because these are the ones that have the qualified scenarios, as have been explained by my colleagues. If we take a quick look at the functional architecture, of course, this is a cloud application which contains, of course, a backend of software components that run the several functionalities. Here we have the query manager, which is the piece of software that makes sure that the queries are created in the language that the different SCDBs speak. But we also have a front end, of course, with different landing pages that we will see next. And also in the exhibition area, we have a live demo for you to enjoy later on during the breaks. These front ends will be the ones that expose the functionality to the user, such as registering as a new user, or if the user is of type SCDB host, like you own a scenario database, you can also join this web page and fill in your details in order to jump into the onboarding process. The main, or let's say the most of the technical challenge was, of course, to interconnect with the existing scenario databases, because they are really heterogeneous, not only in content, but also in programmatic interfaces, so that there was a lot of effort in this project in order to adapt to all these different possibilities in terms of security, access credentials, and APIs. But this was done in this project, and we are happy to have fulfilled the implementation of this cloud platform. The development of this platform was following several storylines that will be documented into the different deliverables of the project, but let's highlight a few of them. The first storyline is onboarding a new user. This is quite a simple thing to understand. There is a web page where you will be logging in, but the important thing is that you as a user should already have your credentials to access the scenario databases of your interest, so that you will specify this information when logging in, so that the Sunrise Data Framework knows what scenario databases you are allowed to access. The second storyline is similar, but when you are already onboarded as a user, you can specify, okay, I am a scenario database owner or host or representative, so that you can also onboard your scenario database into the platform. And this is not so simple process, but eventually this is guided by the web page that we have built. There are still some manual steps to be done, of course. So there is some things that the scenario database hosts need to do in order to join, and that mostly, or in a simplified way, to say you have to adopt the API requirements that we have specified, so that you have to build some REST API endpoints following open API specifications in order to expose the functions that the Sunrise Data Framework expects from the scenario database. But apart from that, it's rather simple, and then you can connect to Sunrise Data Framework, and as a consequence, expose or offer your qualified scenarios to the wider family of Sunrise users. Finally, the storyline number 3 is let's say, the most important storyline or feature of the Sunrise Data Framework, which is searching for scenarios. So searching for scenarios on the SDV is guided by the query UI component, which is a visual component on the web page, which helps the user to build the query according to the specified languages, these ontologies, following, by the way, the international standards, so that the user can create this query with these ODD tags, etc., and then launch or trigger the query against all the scenario databases this particular user has access to. As a consequence, the user will be shown the list of scenarios that have been returned by all of the individual scenario databases, so that the user can then explore this list of scenarios, evaluate their metadata, of course, that is returned by the scenario databases, such as potentially the metrics that have already been computed by the scenario databases host, or maybe some visuals, perhaps some images summarizing the scenario, etc., and many other parameters which are shown at the application side, so that then the user just need to complete the journey, download the scenarios, and go back to the testing environment, whether it is virtual or real scenario. There are several other storylines, but these are the most relevant ones. As I said before, there will be a live demo in the exhibition area, so you can feel free to join us there. And so we can see, maybe we can exercise the different storylines together and see how this looks. Yeah, I think that was my last slide. Thank you very much.
Yeah, so yeah, I didn't mention that yet, but there will be a session for questions and answers at the very end of the day. But since we still have 5 minutes for the break, if there's some one or two questions, those can now be handled.
Sure.
So I think there's a question. Sorry, I have to ask you to use the microphone for that.
Thank you. So Günter Prokop from TU Dresden. Most of the time when you are dealing with data, you are dealing with confidential data. And so you have to ensure kind of a trusteeship in your data storage. Have you thought on this, and is it incorporated in your data framework?
Yes, really relevant question. The idea is that these, say at the beginning, we have devised this framework as a gateway, if you wish. It's only an interface. So we don't store any of this, neither user or content within the within our platform. So we just connect you as a user to the underlying scenario database instances where this sensitive content might happen to be. So the platform needs to be thought as a very thin layer of interfacing. Might look simple, but it was really complex because of the different heterogeneous languages used behind. But yeah, the information is not living in the platform. Just allows the user to connect properly to the storage areas where the data is.
Before we go to that break, I'd like to ask you to follow Laura. Laura will take the group picture that I mentioned before. So let's all follow Laura, look for a good space in front of the exhibition area to take a picture, and then we'll enjoy a nice coffee or lunch break.
One person without consent, he cannot join.
Yeah.
There's one.
Okay. Let's continue with today's program. So the next topic is the introduction to the next block of the stuff, which is called the environment block. And that again will be done by Jason based on the handbook on the touchscreen.
Yeah, so hello again. This is me. I think I didn't introduce myself last time. So my name is Xizhe Zhang, or you can call me Jason. I'm from the University of Warwick in the UK. And in the Sunrise project, we're the task lead of forming this safety assurance framework. So you will be seeing me one more time later on when we dive to the safety arguments part. Yeah, so right now we are in the second main block of the environment. And before I dive into this, I think just to show you where you can go in our Sunrise homepage to access the handbook. If you click on the tools and in the Sunrise handbook 3.1, so if you click on this, it will lead you to our interactive handbook of the safety assurance framework. Yeah, so just in here. Now let's continue our story. So previously we created the scenarios, we formatted them in an adequate format. We stored in individual SCDB, which are connected to our Sunrise data framework. So now we have everything ready to kickstart our actual testing process in this performance assurance workflow. So the first block you see in the environment is called query and concretize. So by the naming, it has two different steps or functions. One is query, and the other is concretization of the scenario parameters. So let's first have a look at the query. You can see first there's an arrow going from the input all the way to the query and concretize. So those are user input, because for the test scenario to be relevant to your system, let's say your system is working on motorway speed, motorway cruise, and then your ODD and the type of behavior is already predetermined for your system. So you might choose the motorway as a road type, and you might even add certain speed limit. So those are part of the input towards this query block. And through this whole set of input, through this query process, we will then interact with our data framework, as indicated by Marcos in the previous session, those relevant tags covering ODD and behavior. And then the matching scenario will then be returned from the individual scenario database, and then it will be presented to you to test. So that's the first part, which is the query. And that's also explain why there's a bidirectional arrow. So going from query to store is carrying this kind of JSON format, which Jobs also mentioned. So this JSON format is a format, and within this format, it carries the text that you select for your ODD and behavior and other requirements. So this whole data is sent into the data framework, and the data framework this arrow is returning a set of scenarios. And as I also mentioned before, the scenario might have different abstraction levels. So you might be familiar with what we call a logical scenario. So sometimes you might be returned, for example, a scenario saying to test a vehicle, you need to drive between 50 to 70 kilometers per hour with other agents doing this and with these kind of weather conditions. So 50 to 70 is not really executable because it's a range in this case. So the next step after the query, we need to concretize to choose a concrete value. So let's assume that we start with 65 kilometers per hour. Then it becomes a concrete scenario, and then we can pass to the subsequent steps. So now in this storyline, we query, we returned, and we concretized a scenario. The next step is what we call allocate. So the Sunrise safety assurance framework is test environment agnostic. So what do we mean by that is to execute a scenario, you have all range of test environment you can choose from, all the way from the most simplistic simulation environment, maybe forms by the lens and the edges and maybe bounding boxes, to maybe more realistic visual and physics simulation, and even to hybrid environment. So you might have a actual vehicle with actual infotainment system and the cockpit, but then with a virtual surrounding, and all the way to later we might see a test track on the real world, and all the way to public road. So all these kind of environments are valid execution environment for our scenario. So allocate actually will assign the scenario based on our testing objective to the right test environment. So in Sunrise, in WP3, work package 3, we have a dedicated tasks, which is specifically designed to have to develop this environment allocation mechanism. Basically, in simple terms, they extract the requirements from the scenarios and also from our test objectives. And on the other hand, they have a ground truth of all the capabilities of all the available test instances. And by matching the requirements to the capability, we are able to find the least effort, least resource intense test environment for that scenario. So, but yeah, feel free to play around with our chat box. You might be able to find this information from here. So that's the allocate. So now we have allocated that scenario also to the right execution environment. And the next step is to execute. So in Sunrise, we have a quite strong emphasis on virtual testing, and we have a dedicated work package specifically focused around simulation framework and virtual testing. What are the main components involved? So that is in work package 4. So if you are interested, please also have a look at our Sunrise deliverables or using the chat box to gather that information for you. So yeah, so that actually is the summarized environment block. So to summarize, to recap, sorry, we use the query, ODD behavior query input, plus other things you might want to associate. Query the data framework, return a scenario, and then we concretize the scenario to make it executable. And then we assign the scenario to a test environment, and then we execute. And then we provide you from Sunrise some simulation framework as a reference for this virtual test execution. And so now I'm going to hand you over to my colleagues who will do a deep dive on the environment block.
So, hello again. Let's start with our deep dive of the environment block. And as with the last deep dive, we have again multiple different topics that we'll look at. So these are the scenario selection or sampling processes. So we'll look at how these how we have tackled this in the Sunrise project on a little bit of a higher level. Then I will give a more detailed example of one specific workflow, how this could work. Focus on one of the workflows. So within this selection and sampling approach, we have tried to develop within Sunrise a family of different methods that can be used depending on your specific requirements and available data. So there's not a one size fits all solution, but of course different partners have focused on different kind of areas of this framework. And I'll just give you one possible example that I'm very familiar with because we at IKA have worked hard on this. So I can present it in a little bit more detail. And then I'll hand over to my colleague who will give a detailed explanation of the other blocks that Jason has just presented. So the allocation as well as the execution with a specific focus on the simulation framework that we have developed within Sunrise. Okay, but let's head back to the scenario selection and sampling. So where have we left off? So we know that we see here these two arrows. So we know that our selection and sampling of scenarios is very related to the store mechanic or the data framework that we have developed in Sunrise. So within this data framework, we are able to query different scenarios and get scenarios in return. If we get or if we're interested in concrete scenarios, so we talked a little bit about this differentiation of the different abstraction levels of scenarios before. Maybe I'll explain this one more time because it's very important for this topic, especially. So let's put the functional and abstract scenarios a little bit to the side for the moment, and mainly focus on logical and concrete scenarios. So logical scenarios are scenarios where you already have a good grasp of the scenario definition and also have the different parameters already defined, but you don't have concrete parameter values. So, but instead you have parameter ranges. So if you think about a cut-in, you know how the cut-in will look like, but you might not know what will be the relative velocities or the relative distances, for example, at which the cut-in happens. So if you put concrete values to these parameters, then you get a concrete scenario. And if you query your scenario databases and already get concrete scenarios in return, and you're interested in these concrete scenarios, that is very good, because these concrete scenarios are really needed in order to feed them to the tests, as we will see later, in order, for example, to simulate them or to have a setup on a proving ground that tries to replicate these concrete scenarios specifically. But what might very well happen is that we end up, after we have created our scenario databases, with a list of logical scenarios. And there might be additional information, for example, some distributions that give us some information on the parameter ranges. But we now need to develop a strategy how to get from the logical scenario that we might have to a list of concrete scenarios that we actually want to test. And depending on what information we have to do this might not really be a trivial process, because of course we don't have infinite resources. So we can't really test infinite scenarios. So then the question becomes, at what part of the scenario space, so the scenario space is that space which is spanned by the different parameter axes or ranges, which part of this space are actually interesting to look at. So where is my pass-fail boundary? So I have defined an evaluation metric. For example, in my cut-in scenario, it might be a criticality metric, as we have discussed earlier, or just a simple binary metric, collision, no collision. And where in my parameter space is the boundary where actually my vehicle crashes and where it does not crash? What parts of the space are uninteresting because it is the behavior of the different actors is very safe. So maybe I don't need to focus on these, but instead focus my limited resources of testing into the more interesting areas closer to this pass-fail boundary. And within workpage 3 of the Sunrise project, we tried to develop different methodologies and tools that allow us to really tackle this problem. And here I have like a two-dimensional parameter space, so that you can have a little bit more of an idea of what I'm talking about. So this comes from one of the use cases. You might have already seen, it's the use case 1.2. You might already have seen the poster during the break. But just as a quick reminder, so for your understanding, in this is the sub-use case D. So this was you're driving onto an urban intersection, and another vehicle is driving also into the intersection and violating a red light. And then in this use case, we are doing some V2X communication so that our CCAM vehicle can get this information that someone is violating the red light and act accordingly. So then it's very interesting now to realize, okay, where do I test? So let's look at now. Let's jump a bit forward. We have already done some tests here. I'll go back where we start in just a minute, but just so we can get a feel for what is happening here. So we have two axes. So these are both the times until the different vehicles reach the intersection in seconds. So both my vehicle as well as the violator vehicle, both at the start of the scenario. So if I set up my scenario so that both times are very low, so both are after like 1 second are already in the intersection, there isn't really much that can be done. As we can see here, the probability for a crash is quite high in this region. So of course there will always be, you can always concept your scenario in such a way that avoiding the crash is not possible. But then if we do one time, if the time to the intersection for one of the vehicles is very high, but for the other one it's very low. So these are these two regions. Here we would expect there to be no conflict, because one car will pass through the intersection unmolested, and then the other one will follow thereafter. So here let's put these regions a little bit back, because of course you can see that there is some crash probability here, which is interesting, but there's a good reason for this. But let's look at this region here in the middle. And this is the interesting one. So this is like the linear relationship. So where at the start of the scenario, the speeds and the distances are set up in such a way that we would have a collision. And if our CCAM vehicle would act appropriately, then we would have here a 0 crash probability. But we can see, interestingly, that our CCAM vehicle still fails in some situations, and which are about like 30%. So in 30% of the cases, even though and the setup so that a crash would occur if no one would intervene, our CCAM system still fails. So that is very interesting. So this is really the region we're interested in to test the vehicle. These other regions are more uninteresting, I would say, because either we are forcing a crash or no crash will ever occur, because the scenario is set up in such a way that isn't really possible. So then we come back to why is here why do we predict some crash probability here? And that comes back to the different methodologies that we use in order to kind of solve this problem. Where do we want to place our concrete scenarios? Where do we want to test? So this is already a very complex model. So let's go back to that in just a second and start a little bit easier. So we have identified some different categories of searching and sampling based on different information that you might have. So for example, one very simple and straightforward way would be to do a combinatorial testing, for example. For this, of course, you need to discretize your parameter space, but then you can just test every possible parameter combination there is. Then you might have already some distributions for your for the different parameters in your scenario, and you might want to leverage these distributions in order to improve like the scenarios that you get. So sample from these distributions, or you might already have and this is the difference between sampling and selection. you might have already a set of scenarios, and you want to select from the set. The rules are similar to sampling. You might also have a distribution over the set. But in sampling, we usually don't have like a defined set, but a continuous range. But these options are always quite limited, especially if you have higher dimensionality, for example. So then within the Sunrise project, we developed some more complex methods that fall under this guided search category. And most of the methods that we looked at really focuses on leveraging machine learning tools in order to improve this sampling process. As I said in the beginning, we don't want to give you a one-size-fits-all solution, but we want to kind of explore all these different possible areas within the framework, and want to give examples and guidelines for all the different methods that you might want to use based on the different requirements you have or the different data you have. So within this kind of methodology, we had different partners focusing on different parts of this methodology framework, I would say. It's our sampling framework, and look at how you can implement methods in order to solve or to implement methodologies that really solve this specific niche. Here are just some of the examples from the different partners. But now I want to talk again a little bit about the picture you saw at the beginning. This was derived using the sampling framework that we have developed based on Gaussian process. That I want to kind of give you a little bit more of a detailed view into, so you understand how this process can work. So as we already discussed, we start with some logical scenarios. So those we get after defining some query based on the ontology that we have. So we might look at, okay, in what ODD do I want to test my CCAM vehicle in? Then get or define tags based on the ontology that describe this ODD. Send these via the formats that we have described and developed to the data framework, which will ask the different databases that you have, that you are authenticated for, or that you are a user of, to return scenarios that fit these descriptions. And so now we have gotten from this data framework one logical scenario. Within this logical scenario, we now have to think about, okay, how do we want to now have or how do we want to perform the test? So then we need to think about what is the kind of metric that I want to evaluate. There we also give some guidelines on what is possible. We always come back to a criticality metric, because that's kind of the easiest thing to imagine. But there are, of course, also other different evaluation metrics that are possible. And this sampling workflow now leverages a surrogate model to improve the sampling process. So what's a surrogate model? That's a statistical model of the evaluation metric. So we're trying to derive a function that looks like how the evaluation metric looks over the parameter space. Of course, we don't, at the beginning, let's assume we don't have any information, so we don't really know how this surrogate model should look like. So we need some initial information in order to construct a first approximation. And this can be done, for example, there are a few different possibilities, but one good possibility is Latin hypercube sampling, where you, and using Latin hypercube sampling, you can ensure a very even coverage of the parameter space with your initial sampling. We have also compared this to random sampling within Sunrise and have found that Latin hypercube sampling is superior in that regard. So this will, given that you have no information, will just evenly distribute a number of concrete points in the parameter space, and you then need to test in order to evaluate these points. So that's a very important topic. We can't really confine this method to just one block in the safety assurance framework. We'll also touch on this a little bit later. But basically, in order to do the smart sampling strategy, you already need to look at all the different blocks. And we also have this error in the safety assurance framework that returns from safety argument again to query and concretize in order to visualize this in the safety assurance framework as well. So this is not, it's not like that you just in the safety assurance framework do one step and then the next and then the next, but instead it's also an iterative process where you might at some point need to go back to a further step and further refine your methodology to improve your results. So let's assume that I have now derived my my first set of concrete parameters. I've tested them in simulation, for example, and I have evaluated them based on the evaluation metric that I have chosen for my test. And then I can use, and then based on these results, I can define a surrogate model that tries to model these results most closely. And the way we want to do this, or we have done this, is using a Gaussian process classifier, which is a machine learning tool that allows you to construct such a surrogate model on data. Then we can run iterative processes by using a optimizer. There are also, again, multiple possibilities, but in this case, we use the Bayesian optimization, which will, based on the surrogate model, determine points in the parameter space that are underexplored, so where the model is not sure how the parameter space looks like, and that goes back to the initial picture we looked at here. So we haven't. So in this case, we haven't put enough test points in these areas to be able to determine if there are any collisions there. So we as experts, we know that there are no collisions there, but of course the model doesn't work like this, and this is why the model predicts, because if it's not sure, it will assume coin flip odds. So this is why it predicts some collision here that is not there. But as you can see, then the optimizer based on this model will now put tell you to put additional test points in these regions in order to further refine the model there, and then we will discover that there are no collisions there. And you can do this process iteratively, and at some point you will realize that the model predictions or the uncertainty of the model will not change anymore. So you'll always have some uncertainty. It's unavoidable. But after after the model prediction does not change anymore, you can terminate this iterative process, and then you have basically over the runtime of this methodology selected your test parameters in such a way that you very smartly put them into regions that are interesting for you. So both to cover the entire space to make sure that there are no collisions in all the different regions of the space, but focusing on the regions you're actually interested in, so the boundary between the path and the failure of the system. So this was a very short overview over our sampling and selection strategy. And now I want to give the floor to my colleague Bernhard to further tell you something about the allocation and execution. Here? Yeah. Okay. Okay. I've just been told that I should do this slide as well. I'm of course happy to do it. After we have defined our specific concrete scenarios, we now have another problem that we face, and that is what test instance, and the test instance here is for example a simulation environment or a proving ground, for example. But which test instance do we now use to evaluate that specific concrete scenario that we have generated using our sampling strategy? And in order to solve this, we have come up with kind of a allocation strategy that uses the test instance capabilities and compares these with the requirements of your specific test or test scenario that you want to do. And we have structured this in a way to follow the ISO ODD specification. And for each element that is defined in the ISO standard, you basically have to explore this like a tree. So we have defined a tree structure, and you have to look at your specific scenario and define certain requirements for all the different components of or leaves in the structure. And then you have to look at the test instances that are available to you and define corresponding capabilities. And then you can use this tree structure to, in a structured way, determine if which of the test instances will fit all your requirements to make sure that you might not miss something vital. And then you should choose, or you will want to choose the lowest cost, and cost does not necessarily need to mean money in this case, because we are talking about human lives, so money is not really an issue, but necessarily an issue. But we are mostly focusing on the cost in terms of time. So it's of course very valuable to be able to simulate more of our concrete scenarios, and using a lower fidelity test instance will allow this. So you should really choose the lowest cost, lowest time cost test instance that is available to you. And then in the validation step, and we'll talk about this in the next safety argument block, we will then make sure that this test instance that you have chosen is actually valid, and catch any errors that you might do and reallocate if necessary. But we'll talk about this later. But now I can then hand over to my colleague.
Thanks, you.
Problem.
So my name is Bernhard Hilpern from Virtual Vehicle, and we will now continue with the execute block. So this block is fairly easy. So as Job just mentioned, as an input for this block, you receive the test cases that have been allocated to either virtual testing, hybrid testing, or real-world testing. And as an output, you will then have the test results that will go to the safety argument. So in Sunrise itself, we focused a little bit more on the virtual testing side. So therefore, we wanted to have a look into a design for a harmonized V&V simulation framework. So the goal is that we don't need to build up a framework for each different use case that we have and build it up from the scratch. We want to have a design that is provides modularity, interoperability, scalability, and of course user friendliness. And so to split it into subsystems for example, a subsystem for sensors, for the environment, for the AD function, to have this modularity and to make sure that we use harmonized interfaces to make it also exchangeable, to make it easy to exchange one sensor model with another sensor model without having to change the whole framework around it. And also it should be extendable. So that means if you shift your focus from one use case to another, it should be easy to extend the framework in each direction you want to have it. So at first we looked into the question, what can we harmonize? And we said we want to harmonize subsystems, data formats, and interfaces. Those are things that can be harmonized. What we definitely didn't want to look into were tools. So it makes no sense to provide any to tell anyone which tools they should use. So there are so many tools in the market, licensed tools, open source tools. And if you're an expert in one tool, you don't necessarily want to use another tool. So this is something that we didn't want to touch. So then we looked into the individual designs of the partner frameworks that they had. We looked at the commonalities there, and we also looked into partner projects and what they did, like Z-Level, V4Safety, or the Architect project, in terms of subsystems, data formats, and interfaces, and we tried to analyze what do they have in common. So what can we learn about this? And then we saw in terms of subsystems, there are certain subsystems that are necessary to be used and some optional subsystems. We learned how should we define the subsystems. We looked into data formats, and we saw here that ASAM family data formats like Open Scenario, Open Drive, Open Label are very commonly used among the partners, and therefore those are the data formats that we would recommend to use within the simulation framework. And in terms of interfaces, we saw that usually the partners used ASAM OSI, especially the 3.x standard. And so this is also something we would recommend to use. And this is then the design that we came up with here in the middle, in this middle rectangle. This is the so-called base layer. Here we have 4 subsystems that are necessary for each use case. So you have sensors, AD function, vehicle dynamics, and environment. And the thing is, if you use a harmonized interfaces, you can make sure that the interfaces between all these subsystems are standardized, and therefore it's quite easy to exchange models within this framework. And then we made sure that this can be extended in each of the directions. So for example, if you want to have a closer look into vehicle dynamics, have some additional subsystems here, like for the powertrain, for the steering, for the braking, that's possible. If you look more into environment, maybe you want to have more focus on traffic simulation or on connectivity, then it's easy to extend it in these directions. Also, when you look at sensors, you can add additional vehicle state sensors or perception sensors. So as I said in the beginning, the goal of this design was to make life easier, to provide help for everyone who wants to build up a new framework. But of course, in terms of the safety assurance framework itself, this design is not mandatory. So if you already have your own framework, it's of course, you're free to use this framework if it's more convenient for you. So in that case, you have your test cases. If this test case is allocated to virtual testing, then use this framework, and then you receive your results, and these results will then be serve as an input for the safety argument, which will then be discussed in the next presentation. Thanks.
Yeah, so it will be me again. So now let's continue this journey. Yeah. Okay, yeah, so hello again. So let's continue this journey. So we have done the scenario, we have done the environment, and now let's have a look at this last block called safety arguments. Safety argument. So so the first step in here, you can see after the execution, we should have collected a set of execution data. And oh yeah. Yeah. So we should already have collected a set of execution data. And this data, the first step is going to pass what we call coverage and test evaluate. I'm going to use an example to explain what they mean later on. Basically, coverage is testing whether we have covered enough of the scenario parameter space, or on the other higher level, whether your scenario, you might not test only a single scenario for your given ODD. You must have, retrieved a set of scenarios. So whether those set of scenario cover your ODD and behavior space sufficiently. So those are what we call coverage, but later I'm going to use a quick example to demonstrate. And then test evaluate, basically for each individual test execution, whether the system passed or failed. And then all of this information will then be passed into what we call safety case. So safety case is where the consolidation of all this analysis outcome come into a single place. And then we reference quite a lot with existing standards and regulations. And then those will be then passed into the last block of what we call the decide, which is going to make the final decision. So we make it quite clear in Sunrise that whatever the decision in the end, it will be a pass or fail binary formed decision. However, you could actually embed certain uncertainty within this pass or fail. So if you put a threshold of certain threshold of uncertainty, then the final outcome can still be ensured as a binary yes or no, rather than a blurred boundary. So now let's use the example that I just quickly came up in the environment block. So let's assume that you are in charge of carry out this performance assurance and come back to the old ODD motorway. Let's add a little bit more details. So motorway, high speed, let's say between 50 to 80 kilometers per hour is your operating speed. And then you can operate on day and night. So we have 4 conditions. And then our first query, let's use the previous scenario. We retrieved a single scenario in this case. Let's assume it's a daytime scenario where the other vehicle is operating at 50 to 70 kilometers per hour. And that scenario will then pass through all this execution. And let's assume that our first point, the concretize, the previous example, we set 65 kilometers per hour. So let's assume that in this case, the system has passed. So that pass is carried out in this test evaluate. So assuming that our pass criteria is to have no collision. So the system did actually manage to not collide at when the other vehicle is at 65 kilometers per hour. So in this case, it passed this test evaluate. But in terms of coverage, we have only covered a single point, 65, across these 50 to 70. So we might not have sufficient evidence to say that the system passed this whole 50 to 70 wider scenario. in that case, at the scenario parameter stage, it might not be sufficient enough. Hence this feedback arrow, and we are using those guidance and the sampling method that mentioned by Jobst. We might actually perform the next concretization of this scenario until we have enough sufficient coverage on this parameter space. But then let's assume that we have explored quite enough on this 50 to 70 and everything passed. Then we come to the second level of the coverage. Let's have a look at the whole ODD. So our ODD, in this assumption, we said the speed is between 50 to 80 and the motorway and day and night. And in this case, we retrieved a single scenario which only corresponding to daytime, and the speed is 50 to 70. So that leaves some holes in our ODD that we are not covering with our scenario. So nighttime, we haven't got any scenarios. And speed between 70 to 80, we also haven't got any scenario to cover those. So in terms of the coverage, in this case, even though we passed 40 in this single logical scenario, but ODD we haven't covered enough. So those will be the consideration that will then be passed into the safety case, and then it will be passed into the decision whether it's sufficient or not sufficient. And in some cases, this feedback arrow will also allow you to actually retrieve further scenarios as well as getting further concretized values for your test. So yeah, so basically this is a very quick overview of these safety arguments, and I think the same as the previous cases, I will hand over to my colleagues to do a deep dive in this safety argument block.
Hello again. So the deep dive for the safety argument block, we have several parts. One is on coverage metrics. I will present that part, but also, yeah, there are two angles of coverage metrics. A bit will be also presented by Jobst. He will probably do a good job there. Test validation metrics and dynamic allocation is also presented by Jobst, and then Olaf will present something on the safety case. First, before going into the coverage metrics, obviously that's used here. Here you see an overview of all the different metrics that are also presented earlier, where they can be used within this safety assurance framework. But actually coverage is not only related to this. You probably also want to know the scenarios that I have stored. How is their coverage related to a certain ODD? And you probably want to know that during the audit phase. And similarly, you probably don't want to know the coverage when you are done with testing, but probably you already want to know that when you are defining your test scenarios. So just want to let you know that it's not just only used here. Then talking about coverage, what does coverage actually mean? You can have a very nice discussion with that, I can guarantee you. If you have 20 researchers, of which 19 are stubborn, I'm not stubborn, so the other 19 are, you will have a nice discussion. What we did, how we define it within the scope of Sunrise is like this. So it's the extent to which a set of scenarios cover the relevant aspects of an ODD. This is not entirely clear on purpose, because then we can also tailor it a bit more to a specific use case. So for example, a set of scenarios, it can refer to multiple things, depending on where you use it in the safety assurance framework. So for example, it can be the set of test cases that you have used within your safety assurance, but it can also be just a set of scenarios that you observed during a drive, or a set of scenarios in the scenario database that you are using to generate your test scenarios, and this list can continue. What does relevant then mean? That's also a very subjective term, and that could mean multiple things depending on the context. So for example, all relevant environmental conditions are covered. All time instances during a certain drive are covered by scenarios. all actors that meet some predefined conditions, or we can also look at a specific parameter space of a specific type of scenario. So actually all these different aspects are covered by Sunrise. And then a very important thing, that's actually, I really want you to take that away from this presentation. What does a good coverage metric mean? Well, first of all, you need to be able to represent it using a percentage. So for example, I see a lot, like we drove so many kilometers. That's not a good coverage metric, because you don't know what is the total number of kilometers I need to have, or the total number of tests, or whatever. So that's not a good coverage metric. And another important thing is that 100% coverage needs to be achievable with practical means. So I also see coverage metrics also in the literature, quite many actually, that only reach this 100% asymptotically. So you only reach it when you go to infinity. And that will never happen in practice. So that's not a good coverage metric. Okay, what are then good coverage metrics? I think maybe also a bit subjective, but okay. Well, we've defined two types of coverage metrics within Sunrise. One is, do the collected scenarios cover all the relevant aspects of an ODD? And type 2, it looks at, do the collected scenarios cover all relevant aspects that we see in a certain test drive or a certain set of data. So type 1 could be, are all weather aspects covered? All weather aspects that part of the ODD, are these covered? And type 2 looks at, given that I have a certain drive, do I see any scenarios that are not covered or any situations that are not covered by scenarios. So for example, you see a cut-in, you see a merge into lane, and suddenly you see something and you have no clue what's happening. That's then you have not reached full coverage. Here are some examples of what we worked on. So for type 1, we developed a tag-based metric. So what we do is we encode all relevant conditions of an ODD through tags. And then we check, do we encounter all these tags within all the scenario categories that we have? If we do not reach 100%, it does not necessarily mean that we need to have more scenarios. So it might be that more tests, more test drives are needed, but it might also be that you have a good justification. So it's not that these coverage metrics automatically tell you, okay, you need to test more or do more. So for example, if you don't see rain in a tunnel, well, that you can probably have a good justification for that. So it's more of a hint where you might need extra arguments or might need more data. For type 2, we have a time-based coverage metric. So it looks at, do I cover all the time instances of my drive with some scenarios? Actor-based coverage, it checks whether all the relevant actors, and then what is relevant, you have some rules to define what are relevant actors. Are these covered by scenarios? And then we also have the actor over time-based coverage, which checks if all these actors are covered at the relevant times. And again, here, 100%, if you don't reach 100%, it doesn't mean that you need, well, it could mean that you need more scenarios to describe all the possible situations, but it might also be that you have some good justification for that. So maybe you encounter a situation that's really far away from your ODD, so you can say, well, I don't need a scenario for that to describe that. Right, then we also have the coverage of this parameter space. It's really a little bit different approach here. And one approach that has been developed within Sunrise is, well, it's a quite complicated approach. I will spare you the details. But the idea is that a parameter space can look very funky, especially if you consider the higher dimensions. And it's a bit difficult to say, okay, what are the parts where we miss some scenarios? So the approach that has been taken here is to transform this bit funky, weird scenario space, parameter space, to to a distribution that we all know. So for example, this very smooth Gaussian distribution, and a factor variational autoencoder is used for that, to transform your parameter space to a parameter space that we know. And then it's actually quite straightforward to check whether you covered all the relevant parts of your parameter space. So that's done in well, there's actually a paper published on this approach. Then we have a few more coverage metrics, but that's Jobst that's going to present this. Here you go.
Thank you. Okay. So thank you for already starting the discussion on the coverage metrics, and I want to kind of continue a little bit the presentation that I gave earlier on the sampling approaches and sampling methodologies, because coverage of these spaces is very related to how we actually choose where to actually test in the parameter spaces. And of course, what kind of coverage metric we choose heavily depends on how our problem looks like. So maybe it is very trivial. For example, here, this example I've chosen as very trivial because we do some combinatorial testing. Of course, there we actually know what are all the options that could potentially be tested are. And if you know all the options, then you can just say, okay, so what percentage of those do I actually have covered? But sadly, if we look at a continuous parameter ranges and a continuous parameter space, this will not be quite so easy. Because on the one hand, it may not make sense, as we have discussed earlier, to put all the test points that you want to look at equidistantly from each other into the parameter space, because some regions might be more uninteresting. So you might achieve already a good enough coverage with a fewer amount of points, and some regions are you need a lot of points because in the scenarios where you are close to the pass-fail boundary, small permutations might actually change the results that you achieve. So there you need to look at a lot more a dense sampling of parameters to achieve the desired coverage effect. So the way that we solve this is actually by leveraging the same method, or I should probably say that this is one way to look at it. Of course, we already presented one possibility to divide the parameter space earlier to achieve coverage, but we just want to highlight a few different approaches. So, and I want to highlight that you can use the same methodology that you use for sampling also to define appropriate coverage and solve this problem that you might not know what number of scenarios are appropriate for coverage in different parts of the parameter space. And so in order to solve this, I think a very good way is to look again at the surrogate model that we discussed earlier. And now this is here now a different scenario than we had earlier. It's a cut-in scenario, and remember earlier we had displayed the collision probability. So that's really the evaluation metric that we are looking at. But here we have now the uncertainty in the model decision. So we're talking about a classifier. So the classifier will want to divide the parameter space in regions of passing and failing, so binary decision. And the uncertainty then represents how how good the classifier can make this decision. And of course, with all stochastic processes, there's always a degree of uncertainty. But we can use this uncertainty in order to define coverage, because regions of high certainty we already have covered quite well. So we can fit, so the model fit is very, very close to the actual, how the actual evaluation underlying evaluation metric looks like. Then we have this pass-fail boundary, which is here marked in black. And then we have a region of uncertainty around this pass-fail boundary. And as I mentioned earlier, it is impossible to reduce this to zero, the uncertainty. But using the amount of tests that we can use, we can use the uncertainty here to estimate, okay, what is how good have we covered the region around the pass-fail boundary, and how is this uncertainty reduced? And we can look at the rate of change in this uncertainty over time in order to come to a decision when we accept this uncertainty as good enough, if the uncertainty does not necessarily change. So why is it that we can't get perfection here? That is because it is not necessarily the case that every scenario that you evaluate has the same outcome necessarily. So it is deterministic. So that depends on your simulation or execution setup. So of course, if you use a simulation and predetermine everything, then you can get the deterministic results. But if you, for example, do a proving ground testing, there might be some small factor that you have not considered, like humidity or temperature of the asphalt, that introduces very small variations that will lead to fuzziness. So which is one reason why you can't really necessarily reduce this uncertainty to zero, even if you try to do that. But you can look at, okay, can I reduce the uncertainty as much as possible, and what are the estimated probabilities for failure, for example, in when I have reduced the uncertainty. Okay, so let's talk a little bit about, and I hinted on this already when I talked about the allocation, and that was that we might make some sort of mistake in the allocation process. So maybe we have missed some important influencing factor, or we have some error in our environment, in our simulation, and our simulation cannot accurately represent what is happening. And we really need to ensure that we kind of capture this before we make a wrong decision. So we really need to validate our results. And in order to do this, we have come up with a validation metric, and very related to this a dynamic reallocation process. So check if my results are valid, and if they are not, how do I choose then appropriate other test instance to continue with my safety assurance process. So how do we want to validate results? And this comes back to really what we talked earlier about the different test instances and choosing the one that is most time effective, which allows us to simulate a larger amount of scenarios. But now I need to kind of check my work, basically. And to do this, I would then choose the next highest fidelity test instance that is available to me. Just one example, maybe we have in our initial allocation process, we have identified that we have a simulation environment that fits all the requirements necessary for us to conduct the test. So we have, and we have then with our sampling strategy found a number of concrete scenarios that we have allocated to this test environment and then tested. Now we might have another test instance, for example, a proving ground available. But of course, testing on this proving ground is very expensive, so we can't really test the same number of scenarios there. But we can leverage this higher fidelity test instance to check our work in the lower fidelity test instance by spot testing. So what this means is that we reduce the number of scenarios that we test in the higher fidelity test instance, and then calculate a correlation between the results in the higher fidelity and the lower fidelity. If this correlation is high, we accept the results of the lower fidelity test instance as valid. If they are not, then we reject those results. So how can we do this? How can we identify these points in the higher fidelity test instance that might be interesting? So there are a couple of factors that we want to kind of focus on, and that is the distance of points in higher fidelity to points in lower fidelity, and especially the variance in the vicinity of potential points that we want to test in the high fidelity test instance, because we're of course especially interested to ensure that in regions of high variance or where the evaluation metric changes or where the uncertainty is high, that there our results are actually representative. And then what you can do in order to determine these points is you first define a set of candidate points that are equidistantly distributed over the scenario space, and then you define some scoring in order to determine which of the points will be chosen in order to be tested in the higher test instance. And the scoring will then be done based on these characteristics of the distance of the points to each other, as well as the variance that you have determined in the lower fidelity test instance. And using this, we can then select a set of points and to be tested, and then validate our results from earlier. So now all of this is kind of located within a larger strategy for dynamic allocation. So because we're already thinking about that, this might already be another of those iterative processes that we have so many of. We want to extend the more simpler allocation process that we have earlier and build upon it to already include situations where you might need to switch between different test instances. And here on the right, you can see a higher level overview of kind of the decision-making process that you would need to do in this dynamic allocation process. And you can follow this decision-making. So, so here on the top, we have our the process of our initial allocation framework as I have presented it earlier. And then here in the lower part are then the decisions for the dynamic reallocation part that you might need to follow to check if check your results from the initial allocation. So is my scenario realization feasible? Have I in my tests actually achieved a big enough safety margin? So not only have my tests passed, but also have they passed with a big enough margin to be acceptable? Do I actually have the ability to validate my results in a higher fidelity test instance? And then we do this validation step that I have talked about earlier, and we calculate the correlation between the different results. And then, as a matter of last resort, if this entire process basically fails and you have exhausted all your possible test instances that are available to you, then first, of course, you reallocate if you have additional test instances. But of course, we might think about the situation where there is really something like an unknown that you haven't thought about, that no one else has thought about, and basically here we have like a breaker in this process for this unknown to make you sit back and think about this entire process again, to identify this unknown with your experts, because of course if those exist, then if these unknowns or errors are in the chain, then you need to fix them before you start the entire safety assurance the entire process of the safety assurance framework again from the beginning. Okay, then I would hand over to my colleague Olaf, who will talk a little bit about the safety case.
Yeah, thank you, Joost. My name is Olaf Omnekamp. I'm with TNO in the Netherlands, and I'm happy to guide you through the last 4 slides that are between you and lunchtime. But actually, we have been working all morning to come to a kind of decision for the safety argument. And we have been collecting all type of information, scenario-based information, to build up a safety case. And that safety case is used to make a decision for a manufacturer, for instance, to determine, is my system ready for handing it over to the vehicle authority to check the safety assessment. And for the vehicle authority to determine, does this vehicle indeed meet the requirements in the regulation, and can I allow it onto the road? And to make that decision in a conscious way, a safety case is built up. And we consider that as a set of documents with the argumentation why the system meets the legal safety requirement. It also may contain not only the requirements that come from the regulation, but also any sort of additional information to substantiate that argumentation. And we have drafted a document in Sunrise with some principles and considerations, and I would like to show some of these considerations in this meeting. Actually, we have been doing that on a kind of abstract level. So this is a high-level document, and it's very worthwhile for all of you to visit the exhibition area and to look to the demos of the use cases to see the practical implementation of how safety cases are built up. And actually, it's not set in stone. It's all building experience to improve on this methodology with time. Yeah, maybe I'm standing here. Actually, if we look to regulation, then there are different type of requirements specified there. And the safety case needs to provide an answer to each of them. So we look to specific requirements. For instance, a vehicle needs to have a minimum following distance in a various number of scenarios. That means that the safety case needs to contain a test matrix looking to each of these scenarios, and per test, the result should be provided. So what is the actual minimum following distance that is achieved there, and a reference. When do I decide that the vehicle passed or failed that test? So in a way, that's kind of easy because the regulation already indicates what are these specific requirements. So you can answer them in the safety case. You also have more general requirements, and a very well known one is the CCAM system shall not cause any collisions that are reasonably foreseeable and preventable. So that's not very concrete. So we need to make sure that we find argumentation, a reasoning, what scenarios can actually be considered as reasonably foreseeable. And for these scenarios, we need to prove that the CCAM system can safely handle each of these scenarios in a way that a human driver could have done that. So that's building that type of argumentation takes a lot of effort. And there's a third type of requirement in the regulation. It's kind of a soft requirement. For instance, the vehicle should aim to show stable maneuvering in lane, both in lateral and longitudinal direction. So in that case, showcasing that the vehicle responds in relevant scenarios in that particular required way might be part of the safety case as well. There are many additional requirements coming from standards. We have not been considering that specifically in this project. I think the added value of the safety assurance framework of Sunrise is that we can start estimating a safety risk and quantify it actually. And the reason is that if we use the safety assurance framework, that we have been building scenarios in such a way that we can use statistics on them. The added value of using safety risk is that it is a concept that is easily explainable and well understood. If we do look to current regulations, then there's no specific level of risk that is referred to, except for the fact that it's a qualitative reference that a system should be as safe as a safe, competent, attentive human driver. Different regulations use different words, but that's where we look at. But now it has become possible to quantify risk actually using these scenario statistics. And that is part of the safety assurance framework. I showed here a kind of example where for 3 types of scenarios, we show the estimation of risk of an not so good ACC system, where we not only determine the risk value, but also the confidence level based on the amount of data that we use to make that estimate. And you see, the more data we include, the more the smaller the confidence interval becomes, and you see the evolution of the risk. Of course, if we do that, then also the safety case should include how did we verify and validate the methods and the tools that we used to set up that safety case. So we need to provide evidence on the reliability of those tools and methods. And that includes the scenario databases that we used and the tools for selecting scenarios. Well, actually, that has been discussed all this morning. Then also the tools for generation of the testing scenarios, the methods for estimating the probability density functions if we do scenario statistics, the way we do the sampling. So coverage is an important factor here. Also, because we not only look to various ways of testing, so we also should validate the tools that are used for that testing. So the tools being used on the proving ground, like the measurement equipment or targets that we use. And for simulation tools and models, of course, we also need validation. And we could, for instance, refer there to the V4Safety project, where we dived into that aspect as well. One thing I would like to share with you, I started this part of the presentation saying that things are not set in stone. So we are searching how to build really good argumentation for safety. I think the way of using acceptable means of compliance helps us in that. So it's acceptable means of compliance are non-binding guidelines that authorities use to help manufacturers to demonstrate compliance to regulation. The fact is that manufacturers may choose alternative means to show that compliance. And we do that because also the current regulation is subject to change. So that's building up the experience both on the side of the authorities as on the side of the manufacturers. And in this way, using the safety assurance framework, we really put in methods and tools to support the definition of additional means of compliance for building up a safety case and making that decision whether we are able to put the CCAM system safely onto the road. And therewith, I come to the end of this part, meaning lunchtime.